Hi everyone, my name is Galen Gilmore and I'm currently a senior in aerospace engineering at Missouri S&T. I'm one of 3 educators involved in leading the Argonia Cup project at Missouri S&T. I'm super excited to show you what we have in store for you, but first, let's head out to the shop to see where it all happens. So, this is the bay, and this is where we do all of our stuff. Let's see if we can pull some people aside and ask them about the project.
All right, there we go.
Hey there, Landon. How's it going?
Good, how's it going?
I'm good. Do you want to tell us a little bit about yourself for the video?
Yeah, sure. So this year, I am a junior in engineering management here at S&T, and also I am the chief educator slash chief engineer of the Argonia Cup rocket.
Cool. So can you tell us a little bit about why our Argonia Cup team is a little bit different than maybe some of the other teams that will be competing?
Yeah, so the thing that makes our team so special is the fact that we use this as a new member project. So this is, other than us, the 3 educators, this is an entirely new member project. So mostly freshmen and people who are brand new to the team.
So can you tell me about some of your roles and responsibilities as the chief educator?
Yeah, so my job is to basically be a mentor and a teacher to all of the new members. And also another big responsibility, obviously, of being the chief is to make sure that the project stays on schedule and that we're doing the work necessary in order for us to get to competition and, well, launch at competition.
Hi, I'm Madeline Stidham. I'm a sophomore in aerospace engineering and engineering management, and I'm the other team educator for Missouri S&T's rocket design team.
So can you tell me more about the team educator position and what it means to be a team educator?
Yeah, sure. So as team educators, our role is to guide the new members through the entire rocket design process, from designing of the rocket to manufacturing to integration, with the ultimate goal of launching at the Argonia Cup competition. And throughout the entire process, we want the team members to learn what they love about the entire process and go explore that in one of our other projects or some teams that we have on the team, like manufacturing or propulsion or aero and recovery.
So now that we've talked to the leadership on this team, let's go talk to the general members to see if we can learn a little bit about the design of the rocket.
Hi, my name is Andrew Schleshman. I'm a physics major here at Missouri S&T.
So can you tell me how you approach the design of this rocket?
Well, first we have to know what our goal is, which was to launch a 2-stage rocket as high as possible with as many golf balls as possible. 2 big rules that we had to work around was that there was a minimum altitude of 9,000 feet and a total maximum impulse of 5120 Newton seconds.
Cool. So can you tell me what impulse is and what that means?
The impulse is the amount of momentum that the motors exert onto the rocket. So that means that with the maximum impulse, our choices were very limited. We couldn't just choose 2 massive motors and go to space or whatever.
So what motor combination did you eventually land on?
For the booster, we chose the L1520, which this is the motor case for it. It has a maximum impulse of 3,700 Newton seconds. And for the sustainer, this isn't the exact one, but it's the same diameter. We chose the J415W, which has a total impulse of 1,300 Newton seconds for combined total of 5,000, just under the limit. We also considered choosing the K2050 for the sustainer, but it didn't maximize our altitude as much as we wanted because it only has a 1/6 of the burn time as the J415W.
Hi, my name is Macy Odom, and I'm currently a freshman studying aerospace engineering.
So now that we know the motor combination of the rocket, can you tell me a little bit more about what else influenced the design of the rocket?
Yeah, of course. So Argonia Cup scores its competitors a little bit differently every year based on factors such as altitude, payload size, and landing precision. This year the scoring is going to be focused on the payload size and the altitude, with more points rewarded for a higher altitude, as you can see in the equation. So before we designed our rocket, we analyzed the score equation, and using some calculations, we determined that the payload size had started to have a less of effect on the score after around 10 golf balls.
So knowing that 10 golf balls is going to be what you're designing the rocket around, how did that influence the design of the rocket?
So with the payload having less of an effect on the scoring, we decided to mainly focus on the altitude. And because we needed a much lighter and faster rocket than last year's design, we knew that the golf balls would need to be held within the nose cone, and this was mainly to help with our stability. So initially we had two designs. We had one with a continuous diameter of 4 inches, and then we had one that had a 4-inch booster that transitioned up to a 3-inch sustainer. So the 4-inch design would have a much higher altitude than last year's 5-inch. And this would be a simple design due to prior knowledge of building it and the amount of time that we had. So the transition design, it would have a higher altitude than our 4-inch design, and while this would have a very positive effect on the scoring, it would be a very complex build for the amount of time that we have. So therefore, we decided to go with the 4-inch design because we felt it was more practical for our purposes. So after making the decision for our design, our previous payload size of 10 golf balls was then bumped up to 15, and while adding only 5 golf balls didn't really have an effect on the score itself, it did increase our stability, which increased our altitude, thus getting us a higher score. Our final predicted altitude is going to be around 12,200 feet, which is going to give us a grand total of 21,000 for our score.
Hi, my name is Aaron Brinker. I am a freshman here at S&T, and I major in electrical engineering.
Wow, so this is a really impressive looking rocket. Can you go through from top to bottom just all the features of this rocket?
Yeah, of course I can. So, right here we have our nose cone, which is going to be containing our payload for competition, and it's connected to a coupler right here. This is going to be containing our electronics bay for our sustainer, and then right here is going to be hold our sustainer recovery system, and then down here will be for our sustainer motor.
So the payload for the competition is golf balls, right? So how are you accessing the payload in the nose cone, and what connections are used to secure them?
Yeah, so right here we have a bulk plate that will help allow our golf balls to stay this way, and then in order to access this section of the rocket, we have screw holes, and then here we have shear pin holes, so that whenever during launch, this section will attach and help our recovery system to deploy. And then right here we have our switch holes for our electronics bay. And so then right here we have our interstage coupler, which is going to be holding our electronics bay for our booster. And then it will also, and then right here is our booster recovery system along with our booster motor.
Hi, I'm Adam Merchiori. I'm a freshman in mechanical engineering, and I'm on the Argonia Cup team.
So can you tell me a little bit about the fins? I noticed that they're very triangular shaped, which I thought was pretty odd.
So we designed our fins with the goal to reach a certain altitude and with a certain stability in mind. So we went for the triangular shape because it lowered the center of pressure compared to most symmetrical designs. And we built them with birch backing and a 3-layer carbon fiber layup.
So Andrew, can you tell me a little bit more about some of the unique features of this rocket?
Yeah, for sure. The first thing is the wiring tubes that we have here that are 3.5 inches. We use them to feed the wires through for the sustainer electronics bay, so that it protects the electronics during ignition and stuff like that, so they don't get burnt out. The next thing is the interstage coupler. This attaches the sustainer to the booster using shear pins, and when it's time to separate, there's black powder charges that break the shear pins and it separates. And the last thing is the nose cone shoulder, which is this piece. Because we're storing our golf balls in the nose cone, we need to actually be able to access into the nose cone to put the golf balls in there. So we can't like epoxy it or anything like that. We have to have a piece that can separate so we can put the golf balls in.
All right, so hello, how's it going? My name is Naquan Johnson. I'm majoring in mechanical engineering, and I'm currently a senior right now.
So Naquan, can you tell me a little bit about the rocket's recovery system?
Yeah, of course. So for our rocket, our focus was to make sure that the parachutes were rightfully sized so that it would hit a descent, so that the rocket would hit a descent rate of 35 feet per second when the sustainer wasn't ignited. And because of this, we would have a 2-foot drogue for the booster and sustainer, a 4-foot main for the booster, but it would be a 5-foot main for the sustainer. And to attach the parachute to the rocket, we will have a 1/4-inch Kevlar cord that will be 150 inches in length for the booster, but 180 meters for the sustainer. And both the drogue parachutes will be released at apogee, and then the main will be released at 1,000 feet afterwards by Jolly Logics.
So can you tell me, Naquan, why 1,000 feet for both of the main parachutes?
So we chose 1,000 feet because it will be high enough so that the rocket will reach a careful descent rate, but low enough so that the rocket will be able to be close to the launch site so we can recover it without any need for search. And because of that, the rocket should reach a descent rate of around 20 feet per second, allowing us to recover the rocket in a reflyable condition.
Hello, my name is Keegan Wade. I'm a freshman here studying aerospace engineering at S&T.
So Keegan, can you tell me about the avionics of the rocket?
Yeah, so the avionics are going to be composed of altimetrum electronics for both the booster and the sustainer. Those will be in charge primarily of the injection, separation, and GPS and recovery. For the booster, GPS won't be used since it's not going to exceed a height of 5,500 feet. So instead we're going to go with a radio tracking system. And along with the booster, those are going to house 2 Easy Megas, which will be in charge of both the primary and secondary ejection charges. And then with the sustainer, we're going with 2 Telemegas. Those are going to be in charge of the ejection, separation, and ignition, and then the second one's going to act as a backup system.
So can you tell me how the electronics will allow the rocket to have a safe flight?
Yeah, so one component of a safe flight is preventing sustainer ignition if it's deemed unsafe. So the electronics will sense if the sustainer is tilted greater than 20 degrees or traveling less than 200 feet per second, and it will inhibit ignition if it's deemed unsafe. A second component of safe flight is parachute deployment. So at apogee, the drogues will deploy, and then at 1,000 feet, the mains will deploy for both the sustainer and the booster, and that'll ensure a safe descent and a softer impact.
Hi, my name is Roddy. I'm a sophomore in aerospace engineering.
Hi, Roddy. So we've seen a lot of people talk about the individual design elements of the rocket,
Yes.
but I was really curious about how that all comes together in a final concept of operations.
So first we will place a rocket on the launch rail. Then the booster ignites and launches the rocket. It's expected to burn out around 5,500 feet. There, the rocket will separate. Then the sustainer checks its ignition and ignites. The booster's drogue will then deploy at its apogee. Then, the sustainer will continue going up until it reaches about 12.8 thousand feet. Then its drogue will deploy. Later on, the main parachute will deploy around 1,000 feet. And finally, the booster will land at around 21 feet per second, and the sustainer about 19 feet per second.
So this is our 2025 Argonia Cup project. It's called Pharoah. I'm super proud of everybody who's put in the time and put in the work to help make this project a future success, and we look forward to seeing everybody at competition. Have a good one.